Okay? So we're going to be dealing with vectors for the next probably, what's today, Tuesday? Probably the rest of this week. Vectors appear in just about every sort of branch of physics that we're going to be dealing with in here. So this is not one of those teach for a week, forget about kind of things. Vectors are always sort of underneath. It's kind of like the math, right? Like it's like I'm teaching adding to you. You're always going to have to be able to add. Okay? It is one of the building blocks. Okay? And so don't think of it as sort of a separate sort of little unit. Think of it as Colin said, sort of a building block, something that's going to be able to use over and over again. And if you don't get it on day one, that's okay. We're going to spend lots of time dealing with this, right? So I found, oddly enough, when I was searching for stuff to watch for today, I found a video. I watched the first couple minutes, and I was, okay, yeah, it's probably okay. So I'm hoping it's good. I got half a feeling it might be boring. So if I stop it halfway, then don't worry about it. The question was, what is a vector? And Riley said an arrow with two directions. Can something have two directions? What do you mean like that? Like to the right and then up? Is that what you mean? You don't know? Okay. Okay. Yeah, I'm not going to show that video again. That makes it way more complicated. Trust me, not nearly that complicated. Easy today. Easy. Okay. You have a handout, right?
Yeah.
Excellent. All right. So a vector is simply an arrow that represents a vector quantity. I kind of cheated a little bit there, right? A vector is simply an arrow that represents a vector quantity. Now, what is a vector quantity? If you need to, I don't know what's on that hand there. On the top of the hand. Yeah, where it says a vector is, right? Okay. So the vector itself is the arrow, but it's used, it's a model for a vector quantity that you can't see. And the length of the arrow represents the magnitude or the size of the vector. The length of the arrow represents the magnitude or size of the vector. Okay, so how long it is important, which is why you need your ruler. And that the direction that the arrow points represents the direction of the vector quantity. The direction that the arrow points represents the direction of the vector quantity. So again, the arrow, the vector, is simply a model for something somewhere else or something that we can't describe, something too big. It's a way to represent it. In reality, that's what a number is too. I'm just going to pause there because I see you guys still writing. When I write the number 4, I'm going to argue that that's a scientific model. What does it mean? It means I've got 4 pairs of scissors, 4 pieces of paper, right? It's just 4. It's a way to describe it. So a vector is simply a different type of quantity, I guess you could say. Here's my favorite part. Vector quantities are simply quantities that have a direction associated with them. Vector quantities are quantities that have a direction associated with them. They have a direction along with them or as part of them. Okay? Here's some examples. I call them the big 4. Displacement, velocity, acceleration, and force. There are others, but those are the most common. Displacement, velocity, acceleration, and force. And I'm going to show you right away how they can have direction. Scalars are quantities that do not have a direction associated with them. Things like mass, time. Are there more there? There's not. Okay? So for example, if I say displacement 10 meters south, that means north, let's say north instead. If I walk 10 meters north, that means that I'm walking 10 meters to the north, right? There's a direction there. Velocity, you're traveling at 85 kilometers per hour southeast. Your acceleration is minus 9.8 meters per second squared down towards the center of the earth. Force, 400 newtons west. Anything that you can put a direction at the end and make sense is a vector. Things like scalars, you can't. Mass. Back there we have a mass set. It has a 1 kilogram mass. We don't say 1 kilogram west. It's just 1 kilogram, right? Time. It's 9:13 south. That doesn't make any sense, right? I mean, time is always going forward. True enough.
Well, it's true.
So here's the first question. Which of the following properties in physics do you think is a vector? I gave you the big four. Which one do you think might be a vector? Speed, density, momentum, or volume? I heard Colin say, it's either what? Yeah, but it's not speed, it's momentum. Speed is a scalar. It is velocity without the direction. Okay? Momentum, though, is your mass and your velocity together. Okay? Let's try this one here. Yeah. Which of the following properties in physics do you think is a scalar? Does not have a direction. Gravitational field strength, density, magnetic field strength, or torque. Not easy. Okay if you get it wrong. I'm not, I get a mark, but I don't use it towards anything, so it's okay. Just think about it. Make an educated guess. Remember, scalars are things that do not have a direction. Which one is a scalar? So 3 out of those are vectors. I sing the Jeopardy song in my head, and if I'm done, then I press stop. Correct answer is B. Well done, you guys. We've been talking about density a lot. What's it measured in? Kilograms per cubic centimeter, or sometimes kilograms per cubic meter, right? But you don't put like south or east or anything after it, right? Good. All right. So back to the notes. Vectors are represented algebraically by a variable with an arrow over it, such as this one for velocity. Okay? So in most modern textbooks, you will see a V with a little arrow over top of it. When you write it by hand, it's usually a V, and then they only usually draw half the arrowhead, kind of like that, just for ease. If you want to draw the whole thing, that's fine. Technically, you should be doing that all the time. I tend to sort of forget about it all the time. Most textbooks will be precise and do it right. In the good old days before sort of desktop publishing, they quite often put it as bold or bold and italics to sort of differentiate it because they didn't have a way to put the little arrowhead. Okay, when representing a vector graphically, you may move the vector any way you like as long as the length and the direction which it points remains the same. Do you guys have that already? Yeah. Okay, so I want you to highlight if you can, even if you just underline. The length and the direction must remain the same. It can be anywhere on the page. And here's an example. The two vectors shown below are considered equal, even though they do not have the same starting points. They do not have to start at the same place. These are equivalent. How come? Because they're the same length and they point in the same direction. It's really no different than me doing this. Yeah, I guess, yeah. Okay, like those represent the same value, even though they're sort of written differently, right? These vectors are the same. Okay? Okay, now, I quite often get the question, what's the unit for a vector? There is none. Vectors are categories. Okay? The unit of the magnitude of a vector depends on the type of vector you're representing. For example, a displacement vector would be measured in meters, velocity vector would be measured in meters per second, acceleration would be measured in meters per second squared, force would be in newtons, blah, 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 blah. Right? There is no unit for vectors. Vectors are a category of quantities. Does that make sense? And before we do that, we have to talk about direction. I think that's what's coming up next. Let me see here. Yes. So vector direction. The direction of a vector can be measured more than one way. So there's really a bunch of different ways, and you have to sort of be multilingual. You have to be able to sort of deal with each one here. The first one example, a man is following a scavenger hunt for instructions. He's to walk plus 35 meters and then minus 10 meters. So it'll be like, 35 to the 35 to the right, and then I'm not really sure why back 10. It seems kind of a bit of a waste of time. His displacement is 25 meters. What's the distance that he traveled? 45. 45. Okay? So what I'm getting at there is that you guys already know this, so I'm not going to spend a lot of time on it. To the right is positive, to the left is negative. So if you're talking about what they call a straight line, there's no other direction, positive to the right, negative to the left, right? You guys know that already? I'm just reminding you. You don't need to spend too much time on that. Okay, here's another way though. These ones might be new to you. An airplane is traveling at 200 kilometers an hour at 40 degrees south of east. Now, before we go any further, north, east, south, west. Never eat soggy wieners. Oddly enough, everyone gets north and south right, and for some reason, about 25% of people are going to get east and west backwards. I don't know why. Okay, so make sure you know that. So if we're talking 40 degrees south of east, so which way do I look first? South of east. I look to the east, and then I go south of it. How much? 40 degrees. 40 degrees south of east. Okay, so you have to look at the last word and kind of almost go backwards. Start east, go towards the south. How far? 40 degrees. No, you can't. If you just say southeast, I'm glad you brought that up, Colin. If you just say southeast, that means exactly 45 degrees. Exactly in the middle. No. Yeah. That's just a convention. Now, there is a third way. If you say east, 40 south, those are equivalent. East, 40 south means look east and then go 40 degrees south. Now, over my years of experience, most students prefer this way, east, 40 south. This was the way I was sort of taught in high school, 40 degrees south of east. You got to be able to sort of talk about both, because they do appear in different textbooks, different ways, right? East, 40 south. Now, one of the main occupations that deals with all this is pilots and air traffic controllers. How easy do you think it would be to talk about like east 40 south and all that when they're talking radio? Would that be confusing, or would it be sort of challenging, do you think? It'd be nice if there was an easier way. Turns out there is. Okay, so you got to be familiar with this. Here's the last. Oh, never mind. We got to do this first. Let's do this. Yeah. Okay. Yay! Right answer is A. Most people got it. 30 degrees north of east. Look east and go 30 degrees. What would this one be? 30 degrees east of north. Okay. Here's the way the pilots do it. A sailboat is moving at a bearing of 210. This method assumes 0, 0, 0 is north and revolves clockwise. So let's go back and let's draw the directional thing again. So 0 is at the top, and we go clockwise. 90, 180, 270. Interesting little tidbit here. When you're landing on a runway, the runways are numbered in this same manner, except it's not. Runways are every 10 degrees. So if you have a runway that's labeled runway 14, then it points in the direction of 140 degrees, which would be where? And that would be 140. So that's what pilots and air traffic controllers use, because they just know what bearing it is. Bearing 140, right? There's no sort of north-south kind of thinking, which way am I pointing? Right? Just a number. Just a number. What would be, if this is runway 14, because you can land on a runway both ways, right? So going this way is 14. What would the runway be numbered going the other way? How'd you get that? Multiply by 2? Can't be. Pardon me? 220? How'd you get that, Danielle? Pardon me? Well, you said 320. How'd you get that? You added 50 degrees. You're right. Okay. So Danielle is right here. So what she did was that's 140. So she knows that this amount in here is 50. So she added 50 to 270 and got 320. Hold on. We'll come back to that. Okay. So here's another question. Which vector is at a bearing of 300? Which one of these is at a bearing of 300? Which one is at a bearing of 300? A? I thought if when in doubt, pick C. Do you like the clickers? Yeah? Isabel, did you hit enter? Still thinking? Okay. Correct answer? Yeah, D. Right? Because there's 270, so it's going to be past that, right? It's going to be how far past 270? 30 degrees. Okay? Okay. Scale drawings are often used to represent vectors graphically. So we're going to get into the drawing right now. For example, a vector of 300 newtons east could be shown as. Okay? So what you do is, okay? So 300 newtons east. Now, anyone not have a ruler or protractor? I have some little protractors here you can come cut out. And I have a few rulers as well lying around. If you need one, come on up and grab one. Okay, so you got your ruler, you got your protractor. Now we're going to start with an easy one. So 300 newtons east. Okay, so we're going to go straight to the east. Do I even need a protractor for this? Not really. Although you should have what I call, are you guys listening? Because I'm teaching here. Here's the learn part. You should have a reference line that shows where to put your protractor. Okay? So you really should have a line that, at the very, very least, a line straight up and down that indicates that's north. Okay, it doesn't have to be very long. I call it a reference line, just a little line, that's north. And then when I put my protractor on to check, like, I mean, if you're off by a couple degrees, then, you know, I can say, okay, well, that's what they've defined as north, and then I go from there. So if that's north, well then, east would be, right over here, right? And now we're going to go 300 newtons. Now, how far do I go to the right? 300? Well, you must have this. You must have a scale. 1 centimeter equals. And I'm going to say this, and I'm making sure it's recorded because I'm going to say it once. No, I'll probably say it a lot of times. You must start your scale with 1 centimeter equals. You must start your scale with 1 centimeter equals. Whatever is first is what's on the paper. So 1 centimeter equals, could we say 50 newtons? Remember, the newton is a unit of force. It's like how much, right? Force. Okay? 1 centimeter equals 50 newtons. So how long is my line going to be? How'd you get 6? Yeah, exactly, right? So it's going to be 6 centimeters long. 300 divided by 50. Okay, so this is going to be your vector. You must put an arrowhead at the end. You must put an arrowhead at the end. Okay? It's as easy as that. It's as easy as that. Okay? Shall we try some? Okay. On the next page, you've got 4 to try. They involve directions and different units. Usually what happens is people get a little bit in trouble at the start and have to do the first 1 or 2. So take 5 minutes, try them. I'll give you the first answer and then we'll move on. So let's have a look at the first one. There might still be some people that are struggling there. Okay, even if you're done the first one, just watch just to make sure you got it right. Okay, so we've got 25 kilometers at 30 degrees west of north. Pick your scale first. Something that works good. Do you want, like, could you write 1 centimeter equals 25 kilometers? Of course, but then your line would only be 1 centimeter long. You want your line, your actual arrow, to be like somewhere between like 3 and maybe 15 centimeters long. So pick a scale that's not too big but not too small, kind of Goldilocks. Okay, 1 centimeter equals 5 kilometers. We got 30 degrees west of north. Draw your reference line. North. I need my ruler. Where'd it go? I need my protractor. Okay, so 30 degrees west of north. So starting from north, it's much easier to do on paper, by the way. So starting from north, from the bottom of that line, see you put the little crosshair right there, right? So I'm going to go to 30 degrees west of north, 10, 20, 30. Okay, hang on. I'm going to go 5 centimeters, right? See how much harder this is for me? Because I got to make this thing go like this. Okay, from the bottom.
But can you also do like 1 inch is equal to?
I prefer centimeters. You can. But we live in a metric society. Okay, so like that. And then we're going to go 1 centimeter equals 5 kilometers, so we're going to go 5 centimeters, right? Oh, I went too far. I went too far. Now, actually, I went too far, and that brings up a good point. Because, is everyone going to get it perfectly, exactly 5 centimeters? Well, you should get it pretty close. But there has to be some sort of, like, grace period kind of thing, right? So here's the rule. You can be out plus or minus, you want to guess? 3 millimeters. plus or minus 3, which means you could be anywhere from 4.7 to 5.3 centimeters. If you can't be within that range, you've got problems. That's pretty generous. There's also plus or minus 3 degrees that you can be out. Okay, so it gives you a little bit of wiggle room. Even if you're done, you guys just watch this. North 12 east, so draw your reference line. It doesn't always have to be north, but you know, at the very least you should do that. Little reference line, there's north. I'm going north 12 and then east. So look north. Put your 0 at north of your protractor. North 12 east, right? So there. Yeah, go away. Come on. Yeah, we'll move up. There we go. Okay. North 12 east, and we're going to go 3 meters per second. This is 15, so it's again going to be 5. Now you'll notice my ruler down there, it gives me a number, so that should be 12 right there. So I can do this. It's not north.
Oh.
This one is 45 newtons, and I did that on purpose. 45 newtons of force at 64 degrees above horizontal. So horizontal simply means flat. So above the horizontal, sometimes abbreviated ATH, above the horizontal. 64 degrees above the horizontal just means from a horizontal line.
Okay, so then you don't have to draw north?
No, because you're drawing horizontal. It doesn't matter which way. So it could either be that way at 64, like so, and then we got 45 newtons, so we need a scale like 1 centimeter equals, we'll say 10 newtons, so I got to go 4.5.
Wait, how did you get 10?
I just picked it. I got any number. It just has to sort of make sense, right? So I got 45 newtons. I want, well, if I divide by 10, then it's going to be 4.5 long, right? Is it starting to make some sense?
If I draw like a whole thing like this, just
You can do that too, Megan, yeah. So I need 4.5. Sometimes your little mark for your protractor is outside that. That's okay. Don't erase it. Like I like to see it, so I know like how to measure, kind of thing, how you did it. Should I do the last one?
No, please.
I'll wait a minute, and then I'll do the last one. Okay, so 8 meters at 175. 175 would be like almost straight south, right? 180 would be there. So you're going to take your ruler. When you do this kind, it's probably best to draw your reference line north. All right, and then we're going to go 175. So put your 0 at north, and we're going to go 175. So from the bottom, and then we're going to go 175 degrees. So there's 170. 175 would be like right there. Right? You can do that too, sure. Some people prefer that, yeah. Yeah. You can do that for a while, and then you realize, I don't need to do all this all the time. Okay, so now it's 8 meters. We still need our scale. So 1 centimeter equals, I don't know, we'll say 2 meters. So that's going to be 4 centimeters long, right? Ah. Move.
That'd be such a good class.
Something like that, right? Okay. Remember to put your arrowheads on. Before I quit, before we're done here, here's some practice ones. You may not have ever seen this thing on the bottom before. Okay, it's called a QR code. You get a QR code reader on your phone. It will read that and send you to a spot on your phone that gives the solution. Okay, I do it lots. So you just scan it and it goes to the solution. If you want to just type it in, it's right there. Okay, it will show you the answers. I'm not assigning it for homework, but these are practice questions. If you think you need more practice, here you go. I'll see you tomorrow.